Alrighty, so going through this here, okay? Again, we start out with acids and bases, and this used to be one giant unit. I've now broken to 3 smaller units. So yeah, we test 2 additional times for a total of 3 on acid-based items, but they're much smaller tests. I used to give out like a 40-question test, and it was a lot. So I break it down, we test more, but I feel like you understand it a lot better once we get out of it. We start off the chapter, and I initially give you 2 definitions of an acid base. We actually have 3 ways that we can define an acid and a base, but we don't talk about the other method until after or at the end of this portion of acid bases. Okay, so we'll see it here actually in day 6 notes. Okay, with this, we have 2 definitions of acid bases. Arrhenius says you either have an H plus to donate, that's an acid, or a base, you have to have an OH minus or a hydroxide to give away. Bad thing about this, there was a number of things that H pluses that could be classified as acids. By saying a base is something that has to have an OH minus, very, very limited substances could be categorized into that. So they came out with this Bronsted-Lowry acid base, and those are the scientists who found it. They said this: you donate an H plus, you're an acid. You accept that H plus, you're a base. Why they redid the definition is more things that showed either acid or base properties could be categorized into this particular section. So more things could be classified as acid and bases. Questions? Okay. All right. So now moving through this, we have our Bronsted-Lowry example here. Okay. We're going to look at our acids and our bases. And it's not really talking about this in notes, but I do want to bring it up right now. We have a 2-sided arrow. So that 2-sided arrow means what? Is it a normal reaction or is it an equilibrium reaction? Equilibrium. So with an equilibrium reaction, we can write down the equilibrium expression, okay? So I want you to do this out to the right here because we're going to write underneath the equation. Let's go ahead, because we're at equilibrium, let's write that equilibrium expression. And so we are going to have big giant K, and from our last unit, we have our equilibrium. What goes on top, reactants or products? Products. It has to either be AQ or it has to be a gas. Well, both of those things, NH4 plus and OH minus, are AQ. So we could say this. We could say, all right, the concentration of NH4 with a 1 plus raised to the first power because of the coefficient of 1 times the concentration of OH minus raised to that first power is all divided by only one thing, NH3. And why don't we include H2O? It's a liquid, okay? So I want you to think acid base, when we get to it, we have some instances where it's equilibrium. So we got to apply what we know. We'll kind of expand on that, but I do want you to kind of get that mindset as we progress forward, okay? Now, let's get down to the business of the notes that are really talking about, okay? An acid donates an H plus, a base accepts an H plus. And then down here, you have a conjugate acid versus a conjugate base, okay? We're going to identify these things, and we call these things acid conjugate base pair, or we have a base conjugate acid pair. And it allows us to look at items one by one in more specific detail, okay? So we have this. I'm going to start out, and I am going to look at NH3, okay? So look at NH3 on the left. and I'm going to go to the right, and I find something really, really similar to NH3, but it's that NH4 plus. So from left to right, did that NH3, did it gain an additional H plus, or did it lose? It gained, all right? If you look back on the previous page, a base is a proton acceptor or an H plus acceptor, meaning from left to right, it gains an extra H. Okay, so NH3 is our base. Well, because NH4 with a 1 plus adds a particular H, down here, a conjugate acid says a proton, aka a proton in us, or for us, is an H plus ion. So NH4, because from left to right, it gained that extra H plus, or a proton is added. This right here is our conjugate acid. Okay, now H2O, it's kind of weird to think about this, but if we look at H2O from left to right, we have H2O, and then we have OH minus. So did H2O gain an H plus or lose an H? It lost, because it gives away its H. We don't think about this, but H2O is an acid. Okay, well, if H2O is an acid, then OH minus is the conjugate what? Very good. All right. So it's really important to identify what is the conjugate acid-base pair, because that helps us set the stage for items that we need to isolate or locate here. Okay, any questions here? Does anybody still need this? All right, so going through this, we actually only have one more example, because that bottom example we just did on the particular previous slide, okay? So we're only going to do the example up top here, and we look up here. We have HNO2 reacting with H2O to form NO2 minus and H3O plus, okay? So first things first that I want to identify is this. HNO2, from left to right, it's going to look very, very similar. We get from HNO2 to NO2 minus. So from left to right, did that H from HNO2 get donated, or did you add an additional H to it? You donated, okay? So our HNO2, it donates the H, and as a result, this forms our acid, or by definition is our acid. Well, its pair here is over here, NO2 minus. It lost an H, and so we have an acid. This that I just highlighted in red is the conjugate what? Very good, conjugate base. Then, in this case here, H2O, if we look on the right-hand side, very similar, goes to H3O with a 1 plus. So from left to right, did H2O gain or lose an H plus? Gain. Because it gained, by definition, the Bronsted-Lowry definition, H2O is a base, which means that H3O is our conjugate what? Very good. Okay. Now, I do go one step further. I do want to go one step further here and talk about H3O. Okay, so I'm going to use the color purple here, and I want to take H3O and kind of run with it. Okay, H3O, this is known as our hydronium ion, and we're going to deal with H3O a lot throughout this entire chapter. H3O in this chapter, we like to shorthand write it. And so you're going to see H3O simply written as just H plus, okay? This items, either H3O plus or H plus, first off, mean the same thing, and then they are referred to as our hydronium ion, okay? And that's going to come really, really important as we get into pH, all right? Now, as a reminder, with this problem here, you need to see the previous page because we already identified the conjugate acid-base pair. Any questions? Does anybody still need them? Good. All right, so moving on here, we keep going with this, okay? With our acids and our bases, okay? Not everything is going to be at equilibrium. In fact, only weak acids or weak bases are in equilibrium. If something's strong, whether it's a strong acid or a strong base, and we have criteria, we have definition, we went over that, and I can get offline with you to help you recognize the strong acids and strong bases. But if you have a strong acid and or base, it says we completely transfer. What we call this is that 100% of the H's ionize. Or simply put, every single one of the H's connected to the Cl breaks off and forms H plus or H3O plus. That means we separate completely from Cl minus. Now, notice here with a strong, and you could put acid / base, that's probably best that you do. But what type of arrow do we have here? Do we have a single-sided or a one-sided arrow for something that is strong?
One.
Yeah, one arrow, meaning we don't go backwards, all right? So once the reaction occurs, it happens. And that's really important to recognize, especially as we start moving more and more into pH. Weak acids, it says it only partially dissociates. When we say partially, we're really meaning like less than 5%, okay? Weak acids, and again, you could tack in bases here, same general concept for this, but how many arrows do we see with something that is considered weak? Anybody? Yeah, how many arrows do we see with something that is weak? We see 2, which means we're at equilibrium. So we have to combine items that we knew about chemical reactions up top with what we have just learned about equilibrium and those 2 arrows. Now, last statement we have here before we move on. If you check this chart's actually pretty cool here. It doesn't put any numbers. The stronger the acid, the weaker the conjugate base is. You could also say the weaker the base is, the stronger the conjugate acid is, all right? So you kind of have flip-flop. If you have something that's strong, the conjugate's going to be weak. If you have something that's weak, the conjugate's going to be strong. And this puts it in that inverse order right here, okay? Questions? Does anybody need this? All right, so we get to water. Now, I don't know if you noticed here, and I didn't really point out, but in our previous examples where I had you identify the acid and its conjugate base and the base and the conjugate acid, we had water in one case act as the base, and then we had water in another case act as the acid. Acid can do that. And because it can do this, it's considered an amphoteric substance, which means in certain circumstances it acts as an acid, in certain circumstances it acts as a base. Now, if we take a look here, and you don't often think about this, and we've had H2O as a liquid reacting with H2O as a liquid, we get, it's weak, 1, we get H3O plus and hydroxide, OH minus. Because it's weak, we can go ahead and we can write an equilibrium expression. All right, so let's go ahead, let's figure this out, or let's think about this here for a second. All right, we're dealing with water, so I'll use blue here. But if I said, hey, write the equilibrium expression for what is given in this example, you would start out with K. All right, now because we're dealing with water, just to specify we're dealing with water, I'm going to call this KW. All right, now KW, or K in general, you guys have told me, is products on top divided by reactants. All right, so let's start with our products. We have H3O plus and OH minus. Are both of those AQ aqueous? Yep, so both of them would be included, and so we'd have H3O plus times our OH minus, both raised to the first power because of the coefficient of 1. We would divide that by our reactants, but do we need to include the reactants in this case because they're both liquids? Okay, so we technically would put that over 1, but you don't see that written over 1. The next thing that I want to do is this. KW, through experiments, they figured out that the actual value of KW is 1.0 times 10 to the negative 14th. And remember, K is unitless there, okay? So it would be given as this. Now, any questions before we turn to that last page here? All right, so what I want you to do is this. Remember this info that I'm putting right here. And does anyone need this before I move on? And we're going to start with this. It says calculate the values of H plus and OH minus at 25 degrees Celsius. Well, I should have led with this, but I'm going to copy and paste. I'm going to copy and paste our value from our last page of notes here, and that was this. KW equals H3O plus times our OH minus. And I'm also going to add this, that KW equals 1.0 times 10 to the negative 14th. And I should have led with this. Remember, K is reported at a certain temperature. This is at 25 degrees Celsius, okay? Now, all I'm going to do is I'm going to replace KW with the actual known, calculated, experimentally determined value, and I'm going to put that where it should go. So I'm going to have 1.0 times 10 to the negative 14th equals, and I'm going to have you think about this. Do we have any idea right at this moment in this particular problem what H plus or OH minus is? No. So if we don't know, what do we do in a math equation?
X.
Yeah, we put them both as X. So my H3O plus, I'm going to say is X times my OH minus, which I'm going to say is X. Okay, so let's consolidate this. We have 1.0 times 10 to the negative 14th equals X times X, which, what is it? X squared, perfect. Now, how do we get X all by itself? Too easy. Take the square root of this value. Now, X, which is equal to H3O plus, and is also equal to our OH minus. If we take the square root of 1 times 10 to the negative 14, anybody know what we get?
1 times 10 to the negative 7.
Ah, very good. Now, 1 times 10 to the negative 7th, because they're in brackets, we could go one step further and we could say, hey, that's molarity. That's our concentration there. All right? Now, I just want you to think about this. And this is how we're going to kind of do the last two problems and end the day here. pH scale. If I said something has a neutral pH, what number is that pH? 7. Something times 10 to the negative 7th. Neutral pH is 7. We're dealing with pure water. Maybe we have some connection, and we do. All right? Bottom line here is this. We can use this formula to solve if we know either our base concentration, our OH minus concentration, or H plus concentration, we can solve for that. Okay, so question number 2 here says calculate the H plus, which just as a reminder, it's H plus or H3O plus. So if you see me interchange that, they both mean the exact same thing. Okay, in something that has a hydroxide or OH minus concentration of 0.01. All right, now we're going to do this. Remember, Kw equals 1.0 times 10 to the negative 14th equals H plus, or if you want to write down H3O plus, it all means the same thing, times now the concentration of our OH minus, which actually has a value of 0.010. And I'll ask you this, how do I get H plus all by itself?
Divide by 0.0.
Very good. Okay. And so let's do this. If somebody wouldn't mind putting 1 times 10 to the negative 14th divided by 0.01, what does our value of our H plus become?
1 times 10 to the negative 12.
Very good. And we would express that in a big capital M for our molarity. All right. One thing I want to point out before we finish this set of problems here, 0.01, it may not seem like a big number, but it's a pretty big number when we consider acids and bases. And then times 10 to the negative 12. That means 11 zeros are out in front. That is quite a small number. So big set of base, small set of acid. All right. Now, our last thing here is this. Similar type of scenario here. We want to calculate the H plus or the hydronium ion concentration in a solution where our OH minus is 1.8 times 10 to the negative 9th. Okay. Now, we plug everything back in. We say 1.0 times 10 to the negative 14th equals our H plus times our value of OH minus, which is 1.8 times 10 to the negative 9th. And once more, how do we get H plus all by itself? Divide by what it is attached. And what do we get for H plus?
It's like, what are we rounding to?
Let's see. I can't remember. Let me.
It's like 5, like, it's not scientific notation, it's like 5.
Let's put it in scientific notation.
5.5 times 10 to the negative 24.
Yeah, and since we had just 1.0, let's just go ahead. Let's use 5.6 to round to 2 sig figs there. So our H plus concentration would be 5.6 times 10 to the negative 6, big M. And again, everything is centered around that pH scale where neutral is 7, all coming from this water business, which we can talk about in a few days. All right. Any questions?